morning, everybody. I'm Evan.
And I'm Kayvon.
And we're from UT Austin, and we're presenting TAGE-SC-L with the code structure correlator. So just to start with a little bit of motivation, as you guys all know, branch prediction remains one of the most significant bottlenecks in single-thread performance. And TAGE-SC-L is state-of-the-art, but still suffers from capacity issues. And one key thing to know is easy to predict branches still consume valuable storage inside of TAGE. So with that, here's a high-level architecture of our predictor. It's a hybrid predictor that consists of TAGE-SC-L, our code structure correlator, or CSC, and a Bloom filter. So TAGE-SC-L and the CSC are linked up in parallel, and the Bloom filter is used to decide which prediction to use. One important thing to note is TAGE-SC-L only is updated after the first CSC mispredict, meaning CSC handles all branches initially, and only after it messes up, TAGE-SC-L starts training.
So I'll be talking about the code structure correlator, or the CSC. So the idea behind the CSC is to predict based on the code structure. So we're completely PC agnostic, and we're going to pick up signals from the actual instruction stream coming in. So one of the benefits of this is that it works on cold things, and then it also works across different branches that have same behavior. So if code is duplicated or just similar in behavior, we'll still pick up those learnings. So the initial motivation for this was by looking at JavaScript JITted code. If you look at something as simple as like a mul, we'll have like 12 billion branches for doing type checks. And so we were trying to pick up stuff like that. Additionally, we're looking for things like inline functions or dynamic code relocations for stuff that get tiered up and tiered down by a JIT. So we settled on features like call depth, a global bias, and then some counts of various branch categories. So for us, we just had far, which means the target's more than 4K away, and indirect, which are indirect branches. So how do we actually use these signals that we want, these features that we want to make a prediction? We settled on an OGL-like predictor. So all the features are used to look up these tables, and then those tables provide a weight. The weights are summed and then thresholded, and that gives us our final prediction. This is updated in the typical OGL style, right? So every branch, regardless of whether or not CSC makes the prediction or TAGE makes the prediction, will update the counters, and then if it's taken, they're incremented, not taken, decremented. So one important question to ask is the feature sensitivity. So in our final configuration, we only had 6 features just to lean out the storage budget, because more storage to TAGE, more better. So you can see our winner of the ablation study, where we just removed the feature and saw how it performed, was call depth. That was our most significant feature. We don't have a sort of smoking gun for the reason why call depth was so good, but our general idea is that in things that are shared across like sort of library functions, they have to have checks that are always going to pass for sort of like bounds checking type things, right? In addition to the CSC, we had a Bloom filter to select between TAGE and the CSC. The Bloom filter starts initially empty, and all of the branches are predicted by CSC. On the first mispredict by CSC, we're going to put the PC of that branch into the Bloom filter, and then at predict time, we'll look up the PC of the branch, and if it's in the Bloom filter, we'll give it to TAGE. This Bloom filter is also looked up on update time. If the PC is in the Bloom filter, then we're going to send the update to TAGE. Another question is why CSC is not in the SC. So the first reason for this is that CSC is trying to get sort of global information that's not indexed based on PC. So all of our weights are kind of static. It's not a set of weights per PC. So we didn't want to have CSC signals, which are PC independent, and SC signals, which are PC dependent, mix and interfere with each other. The other thing is CSC originally was derived as like sort of a cold branch predictor. It ends up it just takes up some easy branches. But when it was a cold branch predictor, the selection logic between TAGE, traditional TAGE, and SC is based on TAGE confidence, which for cold branches isn't very meaningful. So that's why we went with a separate CSC and a separate Bloom filter to select between the two.
Yeah, next I'm going to talk about fuzzing the CSC, TAGE, SC-L parameters, which we know is an important area of work. So the way we ended up doing it was we fuzzed with an evolutionary style deep framework, which really means we just randomly generated some parameters with some heuristics as well. So this flowchart kind of shows the generation of one individual, and we kind of did it with the idea in mind that bigger predictors are usually better. So we fuzzed configurations within 5% of 192 kb. The only kind of wrinkle in this process is this repair kind of function. This is to ensure correctness, and also to, if the steps to make the configuration correct brings it over 192 kb, some kind of weighted random process brings it down back to under 192 kb. And so for us, fitness is the average MPKI, and the best individual, which is the lowest MPKI across generations, is. Finally, here are our results. So our predictor has an average MPKI of 3.46, which is 7.73% lower than the CBP2016. In conclusion, our CSC complements TAGE-SC-L by offloading some easy to predict branches. And it offers a cheaper solution with the actual CSC with the tables taking up 1.69 kb for branches that are easy to predict. In the future, more features could be explored, different training strategies, like different allocation policies for CSC could be explored as well. And importantly, alternatives to the big 20 kb boom filter could be explored. That's it.
Thank you.